So just like we organize qualitative data, we can organize quantitative data, which is numerical data, to visualize the data that we have. So visualizing is key, as you may recall from the organizing qualitative data video, that when we visualize, we can infer things right away. So a graph is always handy. So we had bar graphs, pie graphs, stacked bar graphs for qualitative data. When it comes to numerical data or quantitative data, we have a wide range of graphs. So I'm just going to write them out. So recall quantitative data can be classified further into two types: discrete and continuous. So discrete data is data that's measured as a count, individual numbers. So for example, we have 70, 75, 80, nothing in between. Nothing between 70 and 75, nothing between 75 and 80. We only have whole number measurements. Continuous would simply mean measurements come from the entire real number line. So depending on the type of data that we have, the graph will change. We can't use a graph that would work well for continuous data and try to apply it to discrete data. So commonly used graphs for discrete data are dot plot, and we have stem and leaf plot. These days, there are other types of plots, a whole lot of plots. If you go to Google and just type statistical plots, you could see hundreds and hundreds of plots, done in different ways. But the basic foundation contained only two types, which was dot plot and stem and leaf plot. When we have continuous data, we typically use a histogram or we use a box whisker plot. So histograms, box whisker plots are typically used with continuous data. With discrete data, we go for dot plot and stem and leaf plot. And I'll explain what they are in a bit. So the thing that we have to note about a histogram is pretty much a bar graph for continuous data. So we know what a bar graph is. We know we could get the shape of data from a bar graph, as I mentioned in the previous video, even though there it is not meaningful to look at the shape of data because that is qualitative data. But when it comes to a continuous sample or a continuous data set, then a nicely created bar graph will show you a good shape. So what do I mean by that? Or what do I mean by a bar graph for continuous data? So we have raw data, which is a bunch of observations. And we take those observations and we put it in bins or intervals or classes. And once we put the data in bins, intervals, or classes, we would end up getting a frequency distribution. And we know from organizing qualitative data that if we have a frequency distribution, we can create a bar graph. So this would result in a histogram. And why don't we call it as a bar graph here? Because even though we have bars, here the bars are going to be touching each other. There will be no space at all because we are talking about continuous data on the real number line. So there wouldn't be any space, which is why we call it a histogram. But in short, what is a histogram? A histogram is simply a bar graph for continuous data. So I'm going to start with a sample. We will look at the dot plot and the stem and leaf plot first, and then we can talk about the histogram. So let's consider a sample below. Let's say we have 2, 2, 3, 3, 3, 4, 4, 6, 6, 5, 5, 5, 5, 5, 6. So that is a sample that we collected from some sort of an experiment, some sort of a study, but we have a sample here, and we can visualize this simple data set that we have using a dot plot. And this is discrete data because the observations are whole numbers. We go from 2 to 3, 3 to 4, 4 to 5, nothing in between. So what does a dot plot do? Obviously, it is going to have a bunch of dots. So that's the real number line, and I have the numbers 0 through 7. Now, all I have to do is place dots vertically corresponding to each observation. So first, we don't have any zeros, we don't have any ones, so we move on to 2s. So we have 2 2s. So I'm going to place 2 dots. And in terms of threes, I have 3 of them. Three dots. In terms of fours, I have 2 of them. I have 5 fives. And 3 sixes. Now, if you look at that closely, you may see an underlying shape, just like a shape that I was talking about with a bar graph, even though it is not going to make any sense here because the data is discrete. If I had to draw a dotted line, so nothing here, and then I sort of have that shape. So that underlying shape is important to us. Again, I'm drawing a dotted line because we can't, for mathematical reasons, draw a nice little curve because the data is not continuous. It is rather discrete. So I'm drawing that dotted line just to demonstrate that there is an underlying shape behind the observations that we have. So just by looking at the graph, I can say, well, the observation that is repeating the most is the observation 5. So because it has the tallest or the most number of dots, resulting in the tallest line of dots. So that is the most frequent observation. So the second most frequent observation could either be 3 or 6. And that is a simple dot plot.
I have a question.
So the second type of plot that we use for discrete data and occasionally continuous data is the stem and leaf plot. It works better typically for discrete data, but we can use it for continuous data also. Even though I categorized stem and leaf plot under discrete, do keep in mind I use the word commonly. So I'm going to use a stem and leaf plot both for discrete as well as continuous. Even though it is commonly used for discrete data. So let's consider a sample, a discrete sample. I guess that's good enough. So it is discrete data, and I want to construct a stem and leaf plot. This is also going to be a bit visual, and we can get information just by looking at the graph. So why do we call it a stem and leaf plot? So it has 2 portions. One is the stem part, the other is the leaf part. So anytime we have a stem and leaf plot, the key thing that we need, again, a play on words, is a key. What is the key? The key is going to tell us on how to interpret the data that we see, or the graph that we see. So 1 vertical dash 8 means 18. So if I have a 1 in the stem side, 8 in the leaf side, then I would interpret it as 18. So if the observation is, say, 7, we will have 0, 7, which is 07, which is simply 7. So the key is going to tell us on how to interpret the numbers that we see in a stem and leaf plot. So what I'm going to do is I'm going to start writing 0 and 1, because I don't have other tens. In other words, I don't have any observations that are 20 and 22, 44, 55, and so on. Maybe I will add a few so that you guys can understand this better. So I'll just put in 22, 26, 28, 34, 34, 39, 39, 42, 42, 44, 44, 45, 51, 51, 53. So we'd have 0, 1, 2, 3, 4, and 5. So what are the numbers that we have in the 10th place? So we have a 6, a 3, 2, 4, 4, 5, 7, 7, 8, 8, and that's it. So we're going to take those observations and put it in natural order and write them out. So the key tells us 0 vertical dash 7 would mean the number is 7. So I see a 3, so 0 vertical dash in the middle, 3. So there is a 3 in the data. Oh, but wait, there is a 2. So let's start with the 2. Then there is a 3 in the data. So 0 vertical dash 3. I have a 4 in the data, and I have 2 4s. So 4, 4. I have 1 5. So I'm going to put 5. There is a 6, 6, 2 7s, and 2 8s. Now we move on to the numbers or observations between 10 and 20. Let's see. We have 10, different color. 10, 11, 11, 12, 12, 13, 15, 14, 14, 12, 12, 13, 12, 13. Okay, so we will start with the smallest number, which is 10. So 1, 0 would mean 10. 2 11s, so 1, 1. 2 12s, oh, actually 5 12s, so 1, 2, 3, 4, 5. 3 13s, 2 14s, and 1 15. Now we move on to the 20s, and it seems like there are only 3, which is 22, 26, and 28. So 2, 6, and 8. So I would have 22, 26, and 28. In the 30s, I have 34, 34, 39, 39. So 4, 4, 9, 9. In the 40s, I have 42, 42, 44, 44, and 45. So 2, 2, 4, 4, 5. In the 50s, I would simply have 1, 1, and 3. So all I did is I took the data, I defined a key, and put it as a stem and leaf plot. And do we see a shape here? If you sort of tilt your head and look at it from the side, you would actually see a shape of this sort. So what would that mean? That simply tells us that more observations are in the smaller side, in other words, less than 20, and fewer observations are greater than or equal to 20. So just by looking at the stem and leaf plot, we sort of get an idea that the majority of observations are going to be below 20 and fewer observations above 20. So just by looking at the plot, we can get other statistics, descriptive statistics, such as mean, median, and mode, and etc. We would talk about those just by looking at this plot. But this plot is not effective. Every single plot has a flaw in it. Stem and leaf plot works really well if the sample size is small. It works good for small sample size and discrete data, and it'll work for continuous data as long as they are sort of in the same scale. What do I mean by that? Same scale. Let's just say, or consider this sample. So that is a sample that I have, and you can see every single observation only has the 10th place decimal. So they're all in the same scale, but the data is continuous here. As long as it is in the same scale, a stem and leaf plot is going to work out nicely. Otherwise, you've got to do a lot of tweaking to make it look great. So I am going to define a key. If I see 1 vertical dash 8, to me, it would mean 1.8 as far as this sample is concerned. So I would have a stem part and a leaf part. And we have 1.1, 2.1, we go all the way up to 5. So 1, 2, 3, 4, 5. The key suggests 1 vertical dash 8 would mean 1.8. So I have 1.1, so 1, 1, 1.2, 1.3, another 1.3. So I have the first stem and leaves written out. Now I go to the 2's. I have 2.1, 2.2, 2.2, 2.4. And in the threes, I have 3.4, 3.5, 3.7. I have 3 of them. In the fours, I have 4.2, 4.4, 4.6. In the fives, I have 5.1, 5.1, 5.2, 5.2, 5.3, 5.3, 5.3, 5.3, 5.6, 5.7, 5.8, 5.9. And if you look at it sideways, you'd probably see a shape here. Also, I'll just draw an approximate shape. And it will go down to 0. But you sort of get an idea about the shape. And most of the observations in this particular problem are closer to 5 than they are closer to, say, 1. So if we find an average of this data, it's more likely that it is going to lean toward 4 or 5 than leaning toward 1, 2, or 3. And that bit of information can be easily obtained just by looking at this graph. You don't even need the raw data that we have here. All we need is the stem and leaf plot with a key, and I can look at the graph, stem and leaf plot, and immediately recognize the minimum value of the data, the maximum value of the data. So I look at 1 vertical dash 1, and the key is 1 vertical dash 8 equals 1.8. So it tells me the smallest value in the sample is 1.1. It'll tell me that the largest value in the sample is 5.9, and so forth. So, and that is just a stem and leaf plot.